Hey all, welcome back. Today we're going to be doing some angular momentum free response questions from the 2025 Princeton University Science Olympiad Astronomy exam. This question is about angular momentum, which is really important in celestial mechanics. The main idea here is that when you have a gravitational field, you don't actually have any torques exerted because the gravitational force that's acting on the body is perpendicular to the object's rotational path. And so there's no torques present. And so as a result, angular momentum is conserved, and that'll be really important in solving this problem and in just general celestial mechanics problems. So first thing we're going to do is maybe understand the question a little bit. Here is our asteroid with some initial velocity v naught headed off in this direction, and if there was no mass, it would just go like this forever. But because we have a mass and we have a gravitational force, it's going to change the path of this asteroid to follow this curved path right here. Some important things to note is d is called the impact parameter, which is the perpendicular distance away that this mass would pass by. The distance away if there is no mass here and no forces. If this is the actual distance away right now, this is that perpendicular distance right here. That'll be important for angular momentum conservation later on. And then otherwise, b is the distance of closest approach. So this is the path our asteroid will take underneath the gravitational field influence. And b is that closest distance of approach for that path. Okay, we want to get this derivation later on. And if you guys kind of recognize it, this kind of looks like the quadratic formula. So our initial guess, this looks like the quadratic formula in some sense. And it'll make sense later on as we solve this question. So let's get into it. We have u naught is the asteroid's initial velocity, and then g is a constant. Okay. So first question is mass with velocity v, what is the expression for kinetic energy? So you guys hopefully know this. Kinetic energy, if you haven't seen it before, you can express it as this. And so that's the mass here and velocity there. So that's very simple. And the second question is for a mass m orbiting a mass m at a distance r away, what is the expression for the gravitational potential energy? So that idea is if you have a small mass m or even a big one, and you have a big mass m over here, and these two are a distance r away, there's some gravitational energy contained within the gravitational fields here. And we can write that as this expression, g m over r. And we always make it negative because we treat gravity as a restoring force, and so this object is going to get closer. And so we make the potential negative to indicate that it's going to be coming closer to the other object, restoring in a sense. Okay, so those are our two little expressions right there. Pretty straightforward. Okay, so this question says, assume the velocity of the meteor, or asteroid I suppose, is u during the closest approach to the sun. Write an energy conservation equation that describes the initial and final energy of the system using these variables. So it's an energy conservation equation, so we want to talk about initial energy, and final energy, right? Maybe we can say EG and EI for the initial and final energy. I guess that's kind of a bad idea because we had EI and EF. Okay, that'll be better because we wrote EG up here. All right, so initial energy, let's draw a quick picture. Is initially our asteroid is right here, and it's going to follow this orbit and end up here next to a big mass M. So initial energy is that, we have some kinetic energy associated with the asteroid. So we can write that EK is initially 1/2 u squared, because we have velocity is u during the closest approach. So I think this should actually be u naught squared. And that's coming from the u naught we had drawn up here. Okay, so let's make this one u naught. And then EG, we would write this as negative GMM, and then we have to think about what distance we want to use here. But because the distance is very far away, we can treat this as a distance of infinity. And so when we divide by a very large number for the gravitational fields, we say that the initial gravitational potential energy is basically 0. So that's that given there. Final energy is going to be kinetic still, because we're going to have some velocity right here pointing in that direction. So we can say that EK is equal to 1/2 m, and this time we're going to use u squared, because we have u for the closest approach to the sun, And then we're going to have some gravitational energy here for sure, because we're pretty close to the big mass. And so same expression we used previously, but this time we want to use b in the distance away from these two masses, because we're going to have a little mass right here. That'll be the distance away from them. So we write that because energy is conserved, that's true for the system. We can write this EI equals EF, or 1/2 m u naught squared is equal to 1/2 m u squared minus g m over b, right? And so that's our energy conservation equation. And we can use this later on to actually solve for b, because this looks kind of like a quadratic expression. So we'll do that in a bit. Okay, so next part of it is talking about angular momentum. And so this gives you a definition for angular momentum. Vectorially, it's defined as you don't really need to know this essentially just yet for this problem, but vectorially we define it as the cross product of the radius with the momentum, the linear momentum. And so we write it there. Let's see. Okay, that's fine. Let's see. Cross product, and okay, so we're treating it that in the scalar expression, we can write it as L equals MUR sine theta, where U is your velocity, and R is your radial vector, and then sine theta is the angle between your vectors R and U. So we'll get onto that in a second. First question is, what is the angular momentum of the asteroid with respect to the sun's center of mass at the point where the path is still linear? The point shown with U naught, and at the point of closest approach, B. Okay, so this diagram's right here. To express it again, we can say like we have a little mass m here and a big mass m here. This is our theoretical path, and this is our linear path, right? And so we can write B here. And okay, that looks pretty good. All right, so let's do the initial case, is when the path is still linear, the point shown with U naught. So we have an expression that L is equal to MUR sine theta, right? So we know that mass isn't, this is what angular momentum is, and right now we're doing the initial angular momentum, so we can say Li. So for Li, we know that mass isn't going to change, so that's fine. Velocity is U naught. Let's see. So, and then we need an expression for R sine theta. How do we express this right here? Well, shoot, that's not supposed to happen. Okay, cool. We need an expression for R sine theta. Let's think of it like this. Let's work on our diagram. So this is the distance R away. And we know that if we draw a little triangle right here, from our diagram earlier, we know that this is D, right? And we're talking about the angle between D and R, right? It's kind of shown in this diagram right here. Let's see. So this is D right here, and this is U naught. We're not talking about the angle between D and R. We're talking about the angle between U naught and R, right? So it's going to be this angle right here, the angle between the velocity and the distance away. So we can actually write a little triangle expression, and that triangle expression using trigonometry is that sine theta is going to be equal to D over R, right? So it's the opposite side over the hypotenuse of this right triangle right here. And so if we have sine theta is equal to D over R, then what we can do is we can substitute that back in. And so we have R is the distance away times sine theta, which is D over R. And so these two R's are going to cancel, and we just get M U naught D, which is what we wanted to show for the initial angular momentum. So that's good. Now let's do our final angular momentum. So our final angular momentum is a bit easier, and that's because the sine of theta will actually be 90 degrees. So we're going to erase the sketch real quick. But the basic idea is we wanted the angle between the velocity and the distance away. And that angle is, sine of that angle is given by D over R based off our little triangle diagram. And D was the perpendicular distance we were given away in the initial statement of the problem. The final angular momentum is a bit easier. So we're still going to write MUR sine theta. And at the final angular momentum condition, we have big M here, little m here, and a distance b away. The nice thing is that this is like the direct distance away, and we have that the velocity is pointed in this direction, right? Velocity is pointed in that direction. We kind of got that from the path we drew earlier, is that the velocity is directly perpendicular. So the velocity is pointing in that direction, and the radius away from the particle is b, and it's located in this direction. So when we write our angular momentum, we're going to have m, we're going to have u, and we want r sine theta. Well, the angle right here between these two is actually a right angle. It's 90 degrees. That's the angle between our velocity and our distance, our radial vector outwards. So because the angle is 90 degrees, sine of theta is going to be, we can write this as b for the distance away. This is our r. So we can write this as b times sine of 90 degrees. And the sine of 90 degrees we know is 1, so we can just write this as mub. And that's our expression for the final angular momentum. So the next part asks that using conservation of angular momentum, we want to show this expression, which is pretty simple. We have Li equals Lf for the two angular momentums. So then we have mu naught d is equal to mub. That's our initial angular momentum that we just found. And so cross out the m's, and we get that u is going to be u naught d over b, which is what we want to show, right? So now the final part of the question is saying that using questions 51 and 52, we want to show this result. So let's go back and look at what 51 and 52 are asking us. So 52 is giving us an expression for angular momentum right here, that u equals u naught d over b. So that'll probably be useful. And 51 is asking us, we have an equation for energy conservation. So I'm actually just going to copy and paste those two expressions right here. Okay, so energy conservation equation, and then the second one is that u equals u naught d over b. And this is angular momentum conservation equation. Okay, so maybe what I want to do is, we see that our answer has a lot of u naughts. So that suggests to me that we want to be getting rid of our u's. So instead, we're going to substitute out for this u right here. So 1/2 m, actually, since we can, let's, okay, we'll keep going. There's some variables we can cancel out real quick. 1/2 m, so u squared, which is u naught d over b squared, minus g m over b. Right, now quickly we're going to get rid of these m's, just to get rid of that out of the way. And then we have 1/2 u naught squared is equal to 1/2 u naught squared d squared over b squared minus g over b. Now, what we're going to do for this expression is multiply both sides by b squared. And yeah, that should be good. So multiply both sides by b squared, and then we'll rearrange it a little bit algebraically. So then we have 1/2 u naught squared b squared minus, let's actually do, you can do the algebra and see that this is an equivalent expression. And then minus 1/2 u naught squared d squared equal to 0. Okay, so this is good so far, and now all we have to do is apply the quadratic formula, because we see that this expression is quadratic in b, right? And so applying the quadratic formula, we know that, x is equal to negative b plus or minus square root b squared minus 4ac all over 2a. Quite literally that formula. So we're going to have, in this case, we'll have negative gm. Let's see, is that the sign we want to match with? Yeah, negative gm is fine. Negative gm plus or minus the square root, and this is gm squared right there. Gm squared minus 4 of a, which is 1/2 u naught squared, times c, which is also a negative 1/2 u naught squared d squared, all over 2a, which is going to be u naught squared. And that looks pretty much identical to the answer we wanted. I guess the only thing we have to note is that these 4's and 1/2 are going to go away, and the sign will be positive. So then we can say that we have the square root of gm squared plus u naught to the 4th d squared minus gm over u naught squared, which is exactly what we wanted to show. Okay, so that's the first part of this FRQ for today. If you have any questions, leave it down below. Basic ideas, we talked about energy conservation, angular momentum conservation, and then use some helpful tips that we were given in the problem to go about problem solving. Yeah, but thank you. Take care. Good luck.